Hello everybody. Thank you for coming to my session about pro and cons of clustered indexes. Before we start with the session, two very important things. The operator at the camera. I saw him the whole day and he was sitting there and only slightly moving the camera. Be aware that I need space. So if you sweat, then feel free to take a shower. Okay, zombie attack against clustered indexes. Before we start, a big thank you to all the sponsors of this event. This is the first time in Czech Republic that we have a SQL Saturday here. And to be honest, without the sponsors, this would never happen. So a big thank you to them. Visit them at their booths, and maybe you win some prizes, I've heard. This is me, a little bit commercial, but the most important thing for you to know is my email address. The rest is fake. The email address is the real one. That is my official business email address. And if you have any question concerning the database engine, anything about that, feel free to drop me an email and I promise to answer every single question. What questions I won't answer is, what is the number of my credit number? What is the CVC of my credit number? And what does my wife like best when I'm going out for dinner with her? Any other thing SQL related, feel free. Blah, 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 and go. This is our agenda. Short, but very, very crispy. What is a heap and what is a clustered index? That is the first point what we should discuss about, that you see what the differences are in between both different types of storing data. Yeah, and then we go directly into the demos. So whatever you will see here in this session is, it's heavily demo based. Less slides, more code. And what will I do? I will talk with you about the selects differences, the insert, update, and delete. And I promise there will be some surprising, oh, interesting, what that? I never thought that would be possible. And to be honest, there will be some drawbacks if you're dealing with heaps or with clustered indexes, and this is maintenance. So this is one thing where you should become aware of. What is a heap? Very simple. When I'm doing workshops, I explain heaps as following. Think about your family and they have a 2-year-old son. And if you open the door to his room and look into the cows, that's a heap. That does mean whenever you're searching for something, you have to crawl around the whole room and looking for the things what you're searching for. The problem is that you never ever know whether it is only one piece you're looking for or if you're dealing with more of these pieces. So it means you can't stop if you have grabbed one and say, gosh, I found it. You have to search the whole room. And that's a heap. A heap has a great, great, great benefit instead of a clustered index. It doesn't have a management structure above. Because when you look to a heap, you see only these few pages. These are only data pages. Are you sweating? Huh? Yeah, no? Okay. So you only see data pages. And think about a heap. Okay, everything's fine, yeah. And think about a heap construction. It's very simple. You have only one manager who holds all the things together. This is the so-called IAM page, index allocation map. And if you don't keep it in mind that it's a map, think about a manager, index allocation manager. This is important for a heap. If someone is reading a heap, it first of all has to run a query against the IAM to say, hey, what pages belong to me as a table? Without this, it won't be possible for the SQL Server to know what is the next, oh, it doesn't work, okay. What is the next page? You see that these pages don't have any connection in between. So that means if the SQL Server will read the page 110, where does SQL Server know that page 123 is the next one? That's the reason why SQL Server has, first of all, scanned the so-called IAM and then say, okay, now I got it. I know what pages I have to read. And that's the main difference between a heap and a clustered index. You see, this is a large company. This was a kiosk. This is a company. You see, we have a top manager. We have the middle management, and then we have the leaf level. And you can see here that a clustered index is logically ordered by an order criteria. The leaf level of the index contains the data, and the root node, as a manager, has pointers to the next level. So every single intermediate level will point to the next direction down to the next level. There is only one clustered index in a table because the clustered index is the table. Keep that in mind. Demo time. I show you how it works. Butter. Wow, cool. So, internals of a heap. Can anybody read the little tiny letters in the last row too? Perfect. Seems to be a good session. Okay. So I have a demo database called customer orders, and what I'm doing here is, it's quite simple. This database has no index in it. So all heaps. That's like my home. Everything is in a chaos. So what I'm looking for first is, give me the number of pages which are currently allocated by my table. Look to that we have the total number of pages of 689, but we use only 683 pages. Keep that number, please, in mind. Now, set statistics I own is only that I know how many data pages I will read when I scan the table, and it might be obviously that when I run through a full scan, that the system will automatically read all 682 pages. The question must be, hey, there were 683 page allocated. What is the one page which is missing? The manager. Again, if there is some work, the manager, the first say, okay, do your job. And he's going away, like me. So this is the page which will not come into account. Yeah? Only data pages. What will happen here? When we look to the... No, come on. Okay, here we are. One thing, zoom to fit. What do you say? Good plan? Come on. It is a great plan. We see a table scan, but it returns only one row. That's great, isn't it? No, it is not. The problem is that a table scan does always mean everything. I make it visible. I show you what really is behind the scene, what's working there. And this is, and you know, a short story about when I was 18, I was going to discos. Today we say pub or club. We say club. And maybe you know, when I was 18, it was the first time I got my car. And what won't you do to tell the ladies, hey, I'm a great guy? You take the key of your car and put it on the desk and say, hey, you can come with me. If you're using TraceFlex like that way, I promise you that your manager will never ever ask again whether you are familiar with SQL Server or not. Yeah, that's a good point. So that's the same like the key of your car. This is from a VW. So look what happens here. That is my table scan. Also, I have filter for one. It shows an expansive filter operation in it. A good explanation for what you see here is the following. Anybody or everybody of you is drinking coffee in the morning, right? When I'm drinking a coffee, I stand up, pushing the button, have my mug under it, get the coffee in, go to the fridge, open it, put my milk, and then I enjoy my coffee. That's the normal way. What you will do here is very simple. The delete statement is when you wake up. You take your coffee, and then the filter operation is you call the, how do you say, you call the supermarket and tell them, please bring me 75,000 liters of milk. That's what they're doing. So the truck is coming with 75,000 liters. You are waiting and you're getting one, and the rest you push away. I know here in Europe, milk is very, very cheap. Maybe that's the reason, yeah? But keep in mind, a table scan or whatever scan is the most expansive what you can ever have. And so maybe the execution plan is sometimes cheating you. Easy, isn't it? Next thing. What will happen if I run this? Here is my execution plan. Good plan or bad plan? Be careful. Might be some funny stuff inside. The query was select top 1 star from dbo.customers where ID is equal 10. And it returns 1 row. Very easy because the ID is unique. But whether it's a good thing or not depends on the position where the record is in the table. Scan does mean full scan. But if I look to the I/O, wow, surprise, surprise, 1 I/O. You can never ever get 1 I/O in a clustered index. Will never ever happen because you have a manager over you. Huh? But now see what happened, and that is the point, when I say again select top 1, but with the record which is completely at the bottom of the table. Execution plan, oops. Look to that, it looks good, but 600. So that means whenever you run a select statement against a heap, you can normally never win this game, especially or only when the record is at the top level of your table. I think that's easy. So how does a heap look internally? So what you can see here is, let me size it, is the information about the storage of the data in a heap. And here you see that is the IAM, which manages. And here is my page, my data page, which allocates data. What is interesting, you see no information in the previous or in the next page rows, columns. So that means that all of these pages does not know or do not know what is the next page or what is the previous page. But what I want to draw your attention to is a very important thing. Look always to the page-free space. Page-free space %. This is a value which will only be stored by heaps. Why is the point what I would explain to you later on. So 100% does mean it's completely full. Yeah? But there is a heavy drawback in it. So, and now we look into the IAM page to see what funny things are in. And here you can see, come on, mousy, mousy. Yeah, here it is. So here you can see the IAM, the index allocation map page. Think about what happened in a heap when you run a select. The select statement is querying the IAM page, saying, hey, what pages belong to me? And the IAM returns, well, okay, the first page is the 24,519, and so on, and so on. And then you can see here that the whole page range from 40,000 and X to 40,000 and Y, which is allocated to the table. So for SQL Server, when he reads this information, everything is fine. Now, SQL Server knows what pages it has to read. Simple, simple stuff. So that was what we did. And we go to the next thing. The clustered index is completely different. The clustered index does mean that the data are ordered by a key. I normally explain it like, think about a 15-year-old teenager completely in love, and he or she has invited her spouse or his spouse to his home. Everything will be fine. So whenever he grabs something, he will definitely know that he will find it because everything is in order. And exactly that is with a heap, with a clustered index. But there are heavily drawbacks with that, and I want to show it to you. Internals of clustered indexes. So you have seen the demonstration with the customers table. I now take my customer table and turn it from a heap into a clustered index. Here we are. These are the information we had formerly. We had 689 pages and 683 pages have been read. That was when we had the heap. Now I run exactly the same. It's exactly the same query. Here we are. First of all, look to the plan. Oh yeah, that looks good. There is no table scan. There is a clustered index scan. Ooh, that sounds very, very complicated. Because not only the table, it's an index. Ooh, and someone get afraid of. But here we see 75,000. Well, and now look to this. We have more pages to read. This is a small table. Come on, this is a funny table. We have a large table with orders where are 1 million data in, and you will see the heavy drawback into that table. But here you can see that we have slightly more I/O than we had with the heap. Anybody knows why? Management. Management, huh? The intermediate levels. So that's everything what the system, what SQL Server has to read now. It's in every single company the same. As long as you work alone or with a companion, you normally have very low rates. As more management you get into your company, as more expensive the hourly rates will be, because the management need to be paid too. And that is what you pay when you deal with a clustered index. Go back to SQL Server and see what happens if we change it a little bit. Here we have, so I think most of you are really experienced with that. Come on, Control-Shift-R. So run it, 1 I/O, and this looks very perfect. And here we have, instead of a scan, a seek. Long story short, seek is the best you can ever have, basically. There are some situations where you see a seek, but the system is lying to you. Maybe next year. Anybody here from the organizers? Okay. So let's look what it is. 1 record found. Do you remember how much I/O we had when we were looking for the ID equal to 10 when we had a heap? 1 I/O, right? And now look what a large company is doing with that. Oops, we have 3 I/Os. These 3 I/Os come from one simple reason. SQL Server has to search the whole index structure, traversal, down to the leaf level to get the data. Let's make it visible. I think every single time when you see what SQL Server is doing, you better understand how the system is working from internally. So we do this. Hopefully, yes. So here is my structure. The first thing what I want to draw your attention to is look to the page level. The page level has much more floors than we had with the heap. We have a 2 1s, and lots of zeros. Think about the page level that you say for 0 is the bottom, and as more you get higher, we increase it by 1. So what can we say from here? We can say that the page makes allocated page. Here we are. This page is the highest level in my clustered index, because there is no value which is higher than 2. And now let's together count how many I/Os we get when we want to search for the 10. I start here, but before I start, a short, please draw your attention to the page free space. It's nothing in 100%, blah, 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 and so on, nothing. You will see at the end of the session why this could be a better or not so good possibility when you fill data into it. So we start. Here is my first. This is the page 30,762. Let's go on and look into the root. This is my root node. And what you will see is say the first, a table, a structure like a table, easy to read. Nothing like hex codes, multiple signs you can't read. No, a simple table. And what you can see here is very simple. The system is telling you, hey, come on, this is my ordering key. And if you are searching for a key, then please go to the child page, which is the output near to the value at the left side. So our key is unique. So that does mean in the moment we are looking for the ID 10, what we have to do is we look into the child page ID 30,760 in the first file. Let's do this. Let's check it out. First question while I'm playing around here. How much I/O do we have since now? 1. We were in the root level. Now we go to the bottom, in the intermediate, and again a table. Wonderful, perfect. This is the second level, and the second level is an intermediate level in the same way as the root level. And we have exactly the same structure here. You see that we have the keys and we have the child page ID where we have to point to when we're looking for our value. When I'm going to go into the value 10, what child page ID do I have to go to the next level? Loud. Come on. 30,728. Let's have a look into it. Here we are. Now, how much I/O do we have now? 2. Oh, there must be a bottom. Come on. 3. Oh, hex code, more and more and more. But when I look down to it, go. We were looking for 10. Here is ID 4, 5, 6, 7, 8, 9, and 10. Here's my record. How much I/Os do we have now? 3. And now you see why we have this I/O of 3 in our select statement. The problem here is with the clustered index, as larger your table becomes, as more I/O you will have in a clustered index, because as more levels you have, every single time it has to go traversal through the index step by step by step. It's easier to walk in a 2-level house than in a skyscraper. That's the point. But let's go to the really heavy thing now. Easy? Hope so. A heap uses always a table scan because no index is available. A select on the clustered index is more efficient because an index seek can access directly the search predicates. That's okay. With the top operator in a heap, it can be, but it's not guaranteed that you get less I/O than with a clustered index. Now, primitive groupings, that means you make a select group by, that's definitely a heap is much faster. Yeah? A cluster index has to scan the B tree, and that is the point where we have more I/O than we have in the heap. But now we come to a very interesting thing. Non-clustered index. I hope that everybody knows what a non-clustered index is. I will create one, and this is a very, from my point of view, impressive demo. Yes, I want to save it. Here we are. Here we are. So, long story short, I go back into my customer orders table. Here we are, and what I'm looking for, please have a look to it, it's a heap. There is no cluster in it, nothing in. I'm looking into my customer orders. There are 1 million records in. And I'm looking for all orders coming from the 20th of December, 4 days before Christmas, 2008. Let's see what will the execution plan give me. Here we are. Oh, that's fast. 168 pages, records. And this is my plan. Ooh. It scans 1 million records. That's really much, but we wanted it. And here, let's see what is the I/O. We have scanned this amount of data. Divide this by 128, then you will have the amount in megabytes. Around about 186 megabytes. The system scanned 168 megabytes. So what the developer did now, or will do now, is say, hey, come on, I'm looking for data on the order date, let's create an index on it. We do. Now what do we do? The system is now creating a non-clustered index on the order date. We run the same query again. The first thing what I will do is that you can see what will happen. I run a select only on the order date. Look to the execution plan, and the execution plan is telling you, wow, it's an index seek. Great. Let's see how much I/O we have. Wow. 4 I/Os, 4 pages only. That comes from the B tree, and I have to explain it to you. The date is separated on 2 pages. So then we have 1, 2 in the intermediate level, and then a little range scan over 2 leaf level pages. So that comes the 4 from. But now we run again our query, what we did do the first time. We want to see the customer ID, the order number, and so on and so on. This is my execution, and it runs for 168 records with this execution plan. It looks complicated, but be honest, it isn't. The system is using an index seek on the date, perfect. But what will happen with the data which are not in my index? We have to look for it in the table itself, and that's the RIT lookup, row locator ID lookup. And what the system is doing here is a very simple thing. Anybody of you was flying from Frankfurt? Anybody know the airport Frankfurt? We have very, very much park houses at the airport, 5 or 6 so on. When you drive into the park house, then you first of all has to select one of the park houses, then you drive to the floor you want to park, and then you go for hundreds of thousands of meters until you see a barrier where you can go in, and then at that moment you get a park ticket. And on the park ticket you have 3 informations. What park house you're in, what floor you are on, and what slot you have parked your car. So when you come after 2 weeks back from the holidays, normally my brain is flushed after 2 weeks, then I don't need to remember where my car is because it's standing on my ticket. And that's exactly the same here with the heap, with a lookup. So the system now looks into the table, and here look to the I/O what we have. We have 172 I/Os. Let's do a little math. We have 168 records. 168 times the system was going into the table, getting the data, and then we have left, when we subtract the 168, 4. That's exactly what we had when we were seeking only in the index. So what we can say from this point here currently is that in my execution plan, every single time when SQL Server was looking into the table here, into the RID, it consumed one I/O. Please keep that in mind. 1 I/O. Now, let's go into the index itself. I want to show you how the index looks like. This is my index, my non-clustered index. I only want to take you a little look into the index that you can see what happens. Here is my allocated page. Come on, come on, come on. Here's page level 1. I go into this one, copy. And I look into it, that you can see what happens. Please keep in mind, this is the index, what you see here, on the date. Here is the order date. Do you see this? And here is my park ticket. Ooh, that's hex code. Yeah? But that's what SQL Server is storing and saying, okay, this information I need. And what SQL Server is doing is looking on this ticket and going directly to that position. It's like Monopoly. Don't go over start, don't get 4,000 euros, go directly to prison. And that's exactly the same here with that. With this position, this is my ticket, and SQL Server can directly go to the resource where the record is. And that's incredible fast. Really incredible fast. Now, we come to a point, I will show that later on here, that SQL Server, or that the company who created this database was coming to the conclusion saying, let's hire a consultant. What happened? The consultant was looking to that, and then he comes to the following point, and that is, to be honest, I think that many of you will think so. Every single table need to have a clustered index. These clustered index need to have small values, always contiguous running, that it will increase permanently, small and non-changeable. Right? We say, okay, let's do this. Okay, the party was going on. So the consultant pressed Control E and was running into a horrible disaster. So first of all, SQL Server is making the table a cluster table now. So that means that on the ID we have a unique index, but we have our index on the date. And now we run our query again. How many IOs did we have with the heap? Do you keep it? Do you know it? 172. 172. 172. Let's look to the execution plan. The consultants say, yay, that's so great. We have lost one operation, the bitmap allocation thing, blah, blah. And I look to this, and you say, ooh. If I would be paid by saved IO, let's say €1 per each, then I would throw away the cluster index, take the €300 and say, bye-bye, it was a nice pleasure for you working. What is the problem here? What happened here? Any idea? How do you search data? Oh, I have to stay. Huh? It's okay? Can I go to that? Yeah. It's so funny. He's sweating. Now, how do you look for data? How do you search data in a clustered index? What did I do when I was looking for the ID equal 10? Go through the root page, go through the intermediate level, go to the leaf level. So instead of going directly to a point where my record is, I have to search for my record. So that does mean that now, and I will show it to you, that now the system will not store a ticket where the record is, but a key where we have to look for. And that is the key point here. Here we are. So this is my index, index ID 1. We have 23,000 pages. Let's check it. I did a little mistake. Just a second. No problem. No problem. I get it. We have time enough, hopefully. And I only want to run the... Wenn es mal schnell gehen soll. Where is my page? I'm so sorry for this, but I move down the leaf level. Yeah. Funny. I want to skip it, but please, please, believe me. The SQL Server is now not storing the RIT number, so where the position, but it's storing the key. There is a great, great, great benefit of it, depending on the storage you will consume. The RIT consumes 8 bytes. My ID consumes 4 bytes, but this is very, very often an argument of the people. They say, oh, you have only 4 bytes instead of 8. I say, come on, take a big int, and then what do you store then? It's the same, it's 8 bytes. Yeah? So don't take only care of what you save on storage. Think about what the engine needs to do of work when you are selecting data. And especially when you're dealing with data warehouses. Who is working with data warehouses? Have you clustered index in your fact tables? It depends. That's the best thing you can ever do. Whenever you don't have an answer, say, it depends. That's so easy, and you can earn so much money with that. It depends. Yeah? Okay, let's go. Easy? Hopefully, yes. Let's go to the next thing. So we have in a heap, we have read lookups. The read lookup does mean that we are looking directly for the record itself. You see it here, and you see a compute scalar. The compute scalar does only mean that it has to recalculate the position into a binary value that it can directly go to the dedicated position. That looks like this. So what does SQL Server do with the read lookup? That looks very complicated. Yeah? So, but you see when you have this RID, the read locator, it has a 8-byte information. The first 8 bytes define the page. So that they mean the slot in the park garage where your car is standing. The second 2 bytes is the number of the park garage. And the last 2 bytes are the deck where your car is standing on. SQL Server recalculated, and then you can see that it will then, funny, here it works, but here not. Then you can then see that the system now has the information and moves directly to the position. A key lookup in a clustered index is more expensive because we have a key but not a position. And that does mean for every single record, what SQL Server is looking for, it has to go traversal through the B tree of the clustered index. And that makes it, based on the I/O, more expensive. Yeah? And here, now, forwarded records. That is a funny thing, but before we go to this, I want to show you one heavy drawback with Heaps. This is something, not everything is wonderful in Heap that you say, oh yeah, I love Heaps, I want to have them everywhere. No, there are a few drawbacks. Let's do a little math. I would say that you will now have the first, interesting effect. I go into my DemoDB. You have to switch it to English because I think that you don't know Chinese. So here's my demo table. My demo table is very simple. Let's do a little math. My table has a data length of approximately 2,500 bytes. We can store 8,060 bytes on one page. It is not possible to store half of a record on one page and the rest on another page. Question to you, there is nothing to win. How many pages can we store on one page? 3. Let's check it out. Okay, here it is, that's the math, and you are right, we say 3. I start my transaction, and now you will become aware of my family. This is me, my wife, and my younger daughter. I put 3 records into one page, into the table. I commit it, and let's check what we have. And yes, perfectly, thank you so much, you win nothing, but you are right. Yes? So all 3 records are on one data page. Well done, okay, let's try it again. Before we do this, I want to show you, and this is important for my last demo, not the last yet, but the last at the end. I have 20 minutes, that's cool. Let's have a look to the operations what will happen inside SQL Server when we insert data into a heap. And this is really, really important. Look to this, what happens here. We have the lop format page. Long story short, this means create the page. Then insert a row. But that's not the key point. Okay, it's inserted one row. But then what happened then? This is important. There is a little funny thing called lop. Has nothing to do with lobsters. Lop set free space. And this, unfortunately, breaks the so good standing heap. Why? This lop set free space had the following reason. Do you remember when we were looking into a heap, I said, please have a look to the percentage free space, blah, 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 with a 100%? This is unfortunately the killer here. Why? What SQL Server is doing here, every single time when we add a new row on one page, it has to update a management page in the database called PFS to say, oops, there is one more record in it. And it updates this page maximum 5 times. We have 5 possible values. 0, it's empty. Then 50% is the next value. 50, keep it please in mind because we do a math next. The next is the math. 50%, 80%, 95%, 100. Okay? So, what SQL Server is doing when it inserts the first record, what is then the amount of allocated space in percent? No, there's no value 30, 35 or 33. 50. Okay, 50. If I have 8,060 bytes available, and the first record is in with 4,030, 50%. How much space do we have free? Calculating. 4,030. And now see what happens. The reason why we have all 3 rows stored on one page is only for one reason. It's in one single transaction. And now see what happens with my system when you get aware of the rest of my family. Here, the first one is my older daughter. She's Katarina. She's 22 years old. She loves traveling. Currently, she's in Norway. Here is Emma. This is our first brown fat cat. She's 4 years old. Hopefully, she will not become so old as the previous one. It was 1920. Josie, the second cat. Now we have 3 new rows into our table. Let's look what happens to the allocation. And here we say, oops. This is unfortunately something what can only happen in Heaps. And think about what we did. The first one, when we entered Katarina, the page was empty, okay? Empty does mean how many bytes could we store on the page? 8,060. Okay, we inserted Katarina. Now the system was going to the PFS page, say, come on, I have someone living here with me, and the PFS told me, okay, I've noticed it, 50% is fixed. Now we have 4,030 30 more bytes available. Emma came into the game. Going onto the page, we recorded at the PFS and said, unfortunately, we have another one. The PFS said, come on, hey, have you other hobbies? Looking TV? No? Emma. Okay. The next step now is that we have filled the page up to 80%. When I can store 8,060 bytes on a page, how much do we now recorded, have free on that page? Approximately 1,600. And now comes the third. It's knocking on, say, hey, my name is Josie, meow. But unfortunately, the system is recording here, but you do not fit on that page. And SQL Server allocates a new one. Yes?
You are doing it in one single transaction?
No, but there were 3 different statements, not one statement. This is the problem you have. So if you're dealing with Heaps, so the data warehouse guys, I think when you reload your data warehouse, you're not doing it row by row by row. You're saying insert into select, and then it will not happen. But if you're doing it with each single rows, you will run into these problems. So what does this mean? Conclusion is, if you have table structures which are very wide, like this 2,500 bytes, then it might definitely be better not to use a heap, but instead of that, use a clustered index. And I show you why. Do we have the time? Yes, I have. Okay, let's do it the same, exactly the same with, I have to, this is a new keyboard. Here's, yeah, Heap, good. Now, I do exactly the same. It's the same script. But the difference is that I create a table, same size, with a clustered index. Please think about the following when we are talking about clustered index. SQL Server need to enter the data ordered by the key. It can't work anything in other ways. So what does this mean? Do you remember when we have had a look onto the page allocation of a clustered index, you saw that the page free space % was empty. And I said to you that a clustered index does not need it, because a clustered index need to enter the record ordered by the key. And here we look into it. We go again, 3 records, bam, 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 here we are. Look into what we have allocated, and you see, yes, it's 3, as we had with the heap. Now we do the following. I look again into my transaction, and here what you can see is, let's go here, yes, here we are. Here is my page, which has been a little bit more. So, give a new page, insert first row, second row, third row. But what I want to draw your attention to is this one. Is not this one, no, is, oh, come on. All right, don't see the slot. Yes. So it's not the same script. There is one more field I want to show. Look to this. Here you see it perfectly. Look to this. Slot 1, slot 2, slot 3. So that does mean the records come in with ID 1, ID 2, ID 3, and then now they are sorted that way into the page. And that is the key point. Now I do exactly the same with my 3 other. Oh, come on. So, checkpoint, fluffy change, back and go again. Here is Katerina, 1 statement. Here is Emma, 2nd statement. Here is Josie, 3rd statement. All together is one big family, but all together. But now, think about the following. When SQL Server is putting data into a heap, it doesn't have to go deeply to the page and say, hey, can I live here? It only asks the PFS, please give me some place. When you have a clustered index, the insert consumes more time and more logics, because it has to go down to the page and say, this is my place. A typical German behavior, this is my place. Yeah? And that's exactly the same here. So a clustered index is in that case really expensive. And I demonstrated to you in the, 10 minutes left? 10 minutes only? Hurry up. Okay. You enjoyed so far? Yeah. Easy so far? Logic so far? Yeah. I always think that it's funny insights. Where's my mouse here? So here we go, here we go, here we go. So that was one point. Before I go to the last demo, want to explain something about forwarded records. I can't do the demo because we are running out of time. Forwarded records can only occur in heaps. Unfortunately, they are the most expensive thing whatever you can have. It's like this. A forwarded record will happen if you update a record in your heap and it doesn't fit on the page. It's like me. When I was 20 or 30, my shape was very, very small. But now I'm 52. And you see when you, so from front it looks good, but if you look like, and that's the same with the record. So when a record grows and it doesn't fit on the page, what does it have to do? It has to move to another page. And this happens in this situation. And now think about a postman. A postman in the heap has to bring the post to these houses. The first thing what he had to do was he was going to his manager, the IAM, and was asking for the route. And the manager said, please visit house number 119, then go to 156, then go to 121, and so on and so on. It reads the pages where it has to go. Now the postman takes all the letters and starts walking. It goes to the record number 119. Here it wanted to throw in the letter, but there is a in Germany we say Postnachverfolgungs, what is it? There is a, how do you say, it's a resend that belongs to other English. They're standing, hey, I'm not living here. You have to go to number 156. The postman was a little bit drunken, so he never recognized that he could draw the other letters into this house. What he did was, going with the letter to 156, handed it over. Now we have one IO on the page 119. The second IO on the page 156. Now, because you want to get a clear head, it's walking back. Here it throws in the next letter. Then it goes to 121, 126, 127, 142, and again to 156. When the postman 2 times rings. And that's exactly what happens. So every single time when you have a forwarded record, it does mean that this page needs to be read twice. So when you're dealing with Heap, that you say, oh, Uwe has told so funny things about heaps, I want to have heaps all around me. Please notice that if you have lots of updates in your records and they will increase, do not use heaps. Unfortunately, I love heaps, but in this case, they will more hurt your performance than it will take good things to your performance. Now we come to the last demo. Let's check it. Oh, great. Yeah, we have enough time. Instead of, before we go, one more, clustered index page split. So what we have a forwarded record in a heap is a page split in a clustered index. Page splits are very expensive. You see it in the first time, it stores in a well-formatted or well-formed index, orders 1 to 50 and so on. Now I make an update and 1 increases. What will happen here is that SQL Server will move the half of the data to a new page, but unfortunately at the very, very end of your index. And here happens exactly the same. It goes to page X, moves over, and move back, and starts going on. The only difference is the page at the end will not be read twice. That's the difference. But it consumes lots of transaction bytes, because page splitters mean make a new page, put the half of it, put it away, drop it here, and make new connections, and that takes around 16 kilobytes instead of 8. But how can you prevent page splits when you think about the clustered index? You take contiguous values for a clustered index. That's what you read every single time when you are reading blogs or about how best practice for clustered indexes. Now we follow this best practice. And you will see some funny stuff. High concurrency systems. This is my scenario. I have 3 tables. The first one is called numeric table. There is an identity on it. The identity, so 1, 2, 3, 4, is a clustered index. The second one is, and I think that someone of you will now say, oh, a clustered index on a GUID. You see, they go, oh gosh, no, 16 bytes, too expensive. And the third one is a heap table. Heap table does mean it has no index on it. I have one stored procedure as a wrapper. That means that will do the job for me. And I run this stored procedure by 100 clients at the same time, live, here, on my laptop with 4 cores. It works. Let's see what happens. This is the funny stuff. Heap versus GUID. Here we are. Let me explain what I do. This is a so-called SQL command script. I use it because I want to play around with sizes of columns. So I have the table has the following structure. The field length of my let's say of my column 1, which is only a filler, is 50 bytes. When I take the GUID table, I have to reduce it from 12 bytes because the ID on an identity is an integer, which consumes 4 bytes. The GUID consumes 16 bytes. To be fair, I need to reduce this from the column with the filler. Okay, that's the reason why it is a little bit smaller. So then I create my table, and please have a look here to the table, to the database. It is 2 gigabytes in size, and it will not grow. Really important. Otherwise, when it will grow, it might influence the performance of the insert statement. Let's go for it. Go, 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 go. Here is my log, and I promise the log will not grow either. I put it into recovery mode simple. That's very easy because then I can only restart every single time my next one. Here is my first table. The numeric table is identity, has a clustered key on it, and the C1 column has a fixed length of 50 bytes. Here is my GUID table with a unique identifier, and it is 38 bytes on the column C1. And here is my heap table, which is only with a field length of 50. And here is my stored procedure. This stored procedure is a very, very, very simple thing. I call it DBO proc insert data and say what type of insert I would like to do. If it is numeric, then I insert in the numeric table. If it is GUID, then I insert in the GUID table, and otherwise I insert into a heap table. Simple. And I run a checkpoint after this. That the lock is free. Done. First step was successful. Great. Anybody know about ostress.exe? It's the RML utilities. I can strongly, strongly recommend to use these tools, free from Microsoft, officially from Microsoft. Nothing like, oh, I've heard about something where someone has developed something. No, officially. And what you can do with this ostress is what I absolutely love. You can play around with multi-concurrency environments. I love this tool. And I can really, really, really recommend to use it when you are building large database systems. So now what I'm doing is I am clearing my performance counters. And while the system is running, I want to look for what is my system waiting for. So currently nothing, because there's nothing running. So here is my statement. I connect to my server nbdel13 SQL 16 2016, and I start my proc insert data, and I start with not with the heap. I start, that doesn't make, oh, come on. Super, Ricken, super, you did it wonderful, come on. So copy, work, insert. So I start with the best practice. The best practice is integer continuously and permanently increasing. Let's walk. So the system is now connecting with 100 clients. And what I'm doing now is I'm looking for what is the system waiting here. Write log. That does mean, okay, it's only writing. 100. Come on. Oh, here we have it. That's what I wanted to have. Look to this. First of all, forget about the number of sessions. That's not the key point here. The key point is you see a page/x. And this page/x does mean currently, that is a snapshot, that 2 sessions are dealing for the same resource. It is in database number 6, in file number 1, the page 373. The page number is not the problem. It is that it is a page/. Page/, does mean we want to write exclusive. That is X for that. So that means we have 2 connections which want to access at the same time the same object. Let's see how long it did take. Ooh, 1 minute and 3 seconds. We notice, we write it down. Can anybody read this? If not, no, I make sure that you can read this. 1 minute and 3 seconds. Okay, so before we go to the next step, I want to see what was the system waiting for. Go for it. This is by Paul Rendell here. I love this script. It's, for me, one of the best scripts ever in the internet about the system. Here we have, and you can see that we're waiting for white lock. Okay, absolutely okay, because the system was, unfortunately, I don't have a hard disk with a spindle, it's only SSDs. Yeah? So normally the write log should be in the percentage a little bit lower, but over 99% was permanently writing, but we had page latch access, and they were waiting in total 26 seconds for that. 26 seconds in total, and we had 75,000 times this wait stat occurred. And let's see what the next one will do. Normally, we would say GUID is ugly. GUID. Let's check it out. Before I do this, I will delete the performance counters. Check it out. So we were 1 minute and 3. I now go with the GUID. And go. So while the system is working, let's see what it's doing. Write log, write log, write log. Come on, let's see. I want to see something else. Write log. Come on, come on, come on, come on. There's a page latch. Ah, there we have, but it is different. Why? It's different resources where they are playing with. The first one is the page 1320, and the second one is 1321. Let's see how long it did take. What do you expect? 1 minute 3, more or less? Who say it's more? Because it's a large key. 16 bytes. More. Who think it's less? The rest, huh? Who think it depends? Let's check it. Okay, here we are. Ooh! 18 seconds. Let's check whether we can do it a little bit better. But first of all, write it down. I hope there are a few of you here and say, wow. So now we come to the heap. Before we play that guessing game again, what do you think? Will it be better or worse? Better than the row GUID, or will it be worse? What do you expect? Think about how SQL Server will allocate the rows. Better? Who guess? To be honest, it is a guess. Who will guess that it is better than the row GUID? Great. Who think it's not better? Yeah, it's okay. Come on, yeah. It's not fair. I tested it, yeah? And hopefully the results will always be the same. I cannot guarantee for that. So I tested it a few times, but let's go for a heap. And no. Before I do this, that's like a commercial when you look in TV shows, and he's coming to that, and suddenly commercials. And the same here. Let's see what the system was waiting for. That is important for us before we go for it. So we had write logs and we had page latch X. Here we have, it looked dramatically, but please have a really good look to it. We don't have exclusive logs at the second point. We have shared logs. That means come from a select. Yeah? So what we can see here is that 99.5% is as the same write log. But when we go to the page latch X, it's peanuts. The previous one was 0.5%. Now we are 0.09%. So it's only 20% of that. So now we can go to the results. Heaps. Oh, stop. I have to clear it. Go for it. So that here and heap. So I look for it, right log, right log, right log. Oh, there's a page/x. But it's okay, it doesn't matter. Go, go. Oh, and again. That doesn't look good. And done. Ooh. And 10 seconds. To be honest, I'm surprised. No, really, I'm really surprised. So all my tests were nearby the same as the GUID. The reason why I would expect, me to be honest, I was expecting that it was slower than the row GUID, because for one reason. The system inserted row by row by row by row into the table. And whenever a single row is coming, at what point in the database does it have to say, I'm here? The PFS. That was where the page/x was coming from, not from the index, but from the PFS. The PFS need to be aware, oh, there's a new record in, there is a new record in, and need to upgrade or update the percentage filled information. 2 seconds. It's Ola. Okay. It's okay. That's okay. I thought it was an official one. So let's see what happens here. So it was 10 seconds. Roundabout. Yeah, okay. I was wondering about. So 10 seconds. Amazing, isn't it? So that is one of the reasons why data warehouses are mostly designed with heaps. Or staging tables. When you fill your data warehouse to the expert, I'm not an expert at data warehouses, but I think that your staging tables will prominently be heaps, hopefully. Especially not 1, 2, 3, 4, 5. That was the slowest one. And because, for what reason? That's what I want to show you. Here is a clustered index on the identity. 1, 2, 3, 4, 5. Think about what happened if you insert a new record into a table. At what position does this need to be inserted when we get a new record? At the very end. Because the identity is increasing permanently. What you generate with that is a hotspot. It's the same as when you go, Ola is from Sweden, that's the reason why I name it. When you go to IKEA and you have hundreds of cash boxes activated, but everybody wants to go to the very last because there is the smartest guy sitting there. And that's what you're doing with an identity. So if you have a database where you store, let's say, birthday greetings for the friends of your manager or so on, so let's say once a year, a tiny change in it, use it. Great. If you're dealing with banks and you have high transactional processes, forget about that kind of indexing. So don't use this in a system which need to scale. Why was the GUID so incredibly fast? Because the row GUID was created randomly. And that does mean that now all cache boxes, when we come to IKEA, will be used. So every single random value was on a different page in the index. What is the drawback with that? Page splits. Because when the page is full, there is another one coming in, and then we have a page split. But as always, it depends. If you have mostly index seeks on this index with 1, 2, 3 records, it's completely useless to say, oh, it's page splits. On the other hand, if you run the scripts from Ola every single night, no problem. Yeah? So that is one of the reasons, or that is the reason, or the drawback of this one. It always depends. By the way, and this is the last one, then I finished. Oh, I'm so much over. Identity values mean if you have 1, 2, 3, 4, 5, it does not guarantee that the data will come directly in this order into the table. It depends on the number of cores you have and what number they grabbed. And then you can see here the identity values. The first coming in first, the 11 come in, and then first come the 4th. Sorry, could be a page split. That was it. So I hope that you enjoyed the session and that from now on you would think twice about using clustered indexes with identity 1, 2, 3, 4, and maybe one of you may use heaps instead of clustered indexes. I hope you enjoyed what I told you and wish you a good time. See you maybe next year. Bye.